Welcome to online classes of Ahmadiyya International School. I am Lal Navaratna. So today I am going to continue my solid materials topic, the second part. So we have already completed about half. So the remaining part I am going to complete today. So we will start from the term stress. So under stress, actually when you are talking stress is the simple definition will be force per unit cross sectional area. But when you are just talking about stress, we are going to divide this stress into two parts. One is tensile stress, the other one compressive stress. Compressive stress. So we see what is meant by tensile stress. Tensile stress. Tensile stress, the symbol will be sigma. So when you just take a material in the shape of a wire or rod, and when you apply a force or tension, if the material is extending its length, and if you take the cross sectional area as A, we are defining tensile stress as tensile stress will be tension over cross sectional area. Cross sectional area. So that is sigma is equal to F over A. So SI unit of sigma will be Newton per meter squared, or we can say Pascal. Then base unit of sigma will be, if you just simplify, kg ms minus 2 into m minus 2, when you simplify kg m minus 1 s minus 2. This is the base unit of sigma or tensile stress. Now we see what is meant by tensile compressive. The second one I am going to explain, compressive stress. Compressive stress. Compressive stress. So that means you can just take about a spring, and if you compress the spring, or if you just take a rod and compress, if you apply the force to decrease in length, to reduce the length, if you apply the force to reduce the length, we say as compression. So we are defining compressive stress as compressive stress will be, we can say, compressive force divided by cross sectional area. So same equation, F over A. Same equation we are taking here, F over A. Right, same units, same base units, and same SI unit. So this about compressive stress and strain. Then we are going to study now tensile strain. Tensile strain. The symbol will be epsilon. Tensile strain. So tensile strain we are defining as, if you just take a material and if you apply a tension or the force, if the material is extending, and if you take the initial length as x, so tensile strain we are defining as tensile strain will be extension divided by original length. So strain will be delta x over x. So we can see strain has no units. Only a ratio. Normally strain they are given as a percentage. Strain gives as a percentage. Just example, if they give strain as say 2%, strain as 2%. So that means strain will be equal to 2 divided by 100 or 2 into 10 to the power minus 2. 2 into 10 to the power minus 2, or in another way 0.02. 0.02. So as a percentage or decimal number you can give, but no units. That is tensile strain. So now we see what is meant by compressive strain. Compressive strain. Compressive strain. Compressive strain comes whenever there is a spring, mainly when you apply compressive force. If the spring is decreasing its length, we can say compressive strain is equal to decrease in length divided by original length. Original length. So that is we can say as compressive strain. The same way we can use delta x over x, no units, only a ratio. That is compressive strain. Then we are going to learn Young modulus. Young modulus. Young modulus. In a simple way, Young modulus means the ratio between stress and strain will be Young modulus. So we can define Young modulus as stress divided by strain. So it can be, Young modulus can be compressive stress over compressive strain or tensile stress over tensile strain. You can see it's a constant value Young modulus. It is depending on the material. It does not depend on the amount of the material. So amount of the material or shape of the material, it does not depend. Now that means if you take a thin wire or thick wire, the Young modulus will be same. But if you take thin wire or thick wire, we know that we have learned spring constant or stiffness constant varies. But Young modulus does not depend on the dimensions, right. So Young modulus, we can just get an equation for this. We will take a wire which has original length x and cross sectional area we can take as A. When you apply a force, its extension delta x. Delta x. So Young modulus I can write is equal to sigma over epsilon. So we see that this formula also given in formula sheet. So first SI unit of E will be, unit of sigma will be Pascal, strain has no unit. So same unit, Pascal or Newton meter squared. So SI unit of Young modulus will be this, right. Then you have remember the Young modulus does not depend on the dimensions, it depends on the type of the material only, right. So then we can write another equation for Young modulus. Sigma we can write as F over A divided by strain I can write delta x over x. So we can make this equation into x over delta x. So Young modulus will be F over A into x over delta x. Then we can just arrange this equation like this way, F over delta x, I will write in the same column, and then into x over A. So if we can say that force per unit extension, this part F over delta x will be k. So Young modulus will be k times x over A. You can see that Young modulus depends on the stiffness. Young modulus depends on the stiffness of the material. And you can see the Young modulus is K into X over A. The K will be the stiffness constant, which we have learned earlier, force per unit extension, graph of stress against strain. So we have drawn previous day graph of force against extension. I am going to draw stress against strain. So stress unit we can write Pascal or Newton per meter squared. Strain we can give as a percentage or just no units. So I will take a graph shape like this, just the material, this type of shape we will take it. We will take 5 important points. I will take A, B, C, and then here I will take D, and I will take here as E. And you can see up to elastic limit. Up to elastic limit we can take about this region as elastic region, and this will be plastic region. Right. From this equation, now we see that how we can get from here. We see what is meant by this point A. The point A will be, we can say, limit of proportionality. This A we call as limit of proportionality. A we call limit of proportionality. So we have learned this one under force extension graph very similar way. Limit of proportionality means up to this point material obeys Hooke's law. Up to this point material obeys Hooke's law. So that means straight line part gradient. If you just calculate the gradient of this straight line part, gradient will be equal to stress divided by strain, and that is Young modulus. So up to a straight line and gradient will be equal to Young modulus. There are many past paper questions they are asking, so we have to select the straight line part and find the gradient. Then we see what is meant by B. So B we denote as elastic limit. So elastic limit also we have learned last day. Elastic limit is the point up to which when applied force is removed, the material will regain its original shape and size. So that is we call elastic limit. Then we will go to C, that is we call yield point. Yield point is a point we have learned actually. For small change in stress, there will be a large change in strain. That is the point. At that point, if you just change the stress by small amount, the strain will change by large amount, or extension will change by large amount. So we can say that that is the point, or that is the extension where there will be a considerable change in extension when you apply a stretching force. So you can see the yield point is the point where when there is a small change in stress, there will be a large change in strain. Then we will go to D. D we haven't learned previous day. D we call as ultimate tensile stress. So sometimes we say UTS, or sometimes we say sigma U. Okay, ultimate tensile stress, or ultimate tensile they say strength also. Right. You can see we are defining as it is the maximum stress the material can withstand before breaking. It is the maximum stress the material can withstand before breaking. right. Then we see what is meant by E. That is, E we are defining as structure stress, or we can say breaking stress. That is actually we can fracture. The fracture is occurring in that place, so we can say that place as fracture stress or breaking stress. That is the point where the breaking, the point, the curve, or we can say the wire breaks. So that point we can say as breaking stress. We can say as fracture stress or breaking stress. Breaking or fracture stress. That is a point which corresponds to breaking stress. Right, now you know about the shape of this graph. Actually this bend comes because of the change of molecular structure. When you apply the force, there will be some, when you apply the force, there will be some change in strain due to the force. Molecular change of the material gives this curve down like this. Then I am going to explain as an experiment, we are going to learn as an experiment, we can say experiment to investigate the relationship between sigma and epsilon, to investigate relationship between sigma and epsilon, or to determine we can say Young modulus. So both we can do, we can first get the relationship and then we can find the Young modulus. So this diagram actually we are using, so maybe you have learned this one in the class. You can see, I will just use this is a tabletop, and then you can see here we are keeping a wire compress using wooden blocks, and we can clamp this one. This is we call G clamp, and this is the wire, and then here there will be a pulley which is fixed at the end. You can see the wire straight we go, and here we are keeping some weights, and the down we are keeping some safety form. We are using something like mattress or some sand tray or something, we can keep it, sand tray or something like a form we can keep to protect fall into the to avoid fall into the foot. And then these are weights, and then we are keeping a meter ruler to measure the length, meter rule. This is meter rule, and we are keeping small piece of tape, we can say small tape, a mark. That mark will move with the force, okay? That's why we are using. So we can measure the initial length. First the initial length we can measure. I will mark the initial length from, say, from the wire. We want to measure the extension of this wire. This is the initial length. So when you are doing this experiment, what you have to do, we have to measure, first measure initial length of the wire by using meter rule. Initial length, that is from the wooden block to the tape we can measure. Then we can measure average diameter. We can measure the diameter of the wire from three positions of the wire we can measure. say D1, D2, D3. Then we can calculate the average diameter, D1 plus D2 plus D3 divided by 3. Then area will be pi D average divided by 4. This is cross-sectional area. Right. So then what in this experiment what we are going to do first, for known mass, we can say for a known mass, measure corresponding extension. That means you can just say, as you are keeping here 100 grams, and for that 100 grams how much this paper rider or this tape or small mark is moving, that is delta x, we can measure. So then we can vary, repeat the experiment for different m values. We can get many readings, different. So then table m kilograms, then force mg Newton, and then extension meters. This is, then we can work out sigma will be F over A Pascal, then strain delta x over x. So we have already measured the initial length from meter rule, and delta x we are measuring for different masses. So you can get epsilon value. Then now we have the value sigma and epsilon, then we can draw a graph. The graph will be, our equation will be for Young modulus E equals sigma over epsilon. So sigma will be E times epsilon. This is y equals mx. So we can plot the graph, plot a graph of sigma against epsilon. So you can see the graph, the shape of the graph. This is Pascal, this is no units, straight line through origin. From this graph, gradient gives Young modulus. So you can see that very accurately we can calculate Young modulus. And this experiment, very common experiment which asked in EDEXCEL exams. Then students, now I am going to explain. Now we have learned, we see that from the graph, again I will just go to this graph of sigma against epsilon. So we can see it comes sigma Pascal, this is no units. So this graph we have drawn using this equation. So sigma is equal to E epsilon, this is y equals mx, and we know that this is sigma and this is epsilon. Gradient gives Young modulus. Then what is the area under the graph? See this area. What is given by the area under this graph? Area under the graph will be half stress into strain. So that we can just work out like this way. Half stress will be F over A, strain will be delta x over x. So I can work out like this way. Half F into delta x divided by A into x. Now when you just take the material, if I draw here, you can see when you apply a force, this is the original length, and then cross-sectional area will be A, then delta x will be the extension. So half F delta x means energy stored. We have learned that is energy stored or work done, or we have learned as elastic strain energy. We can say this part as energy stored. divide by A into X, cross sectional area into length gives volume, that gives volume. So we can say as area gives energy stored per unit volume, we can say energy stored per unit volume. This is we call as energy density. So area under the graph gives energy density. So unit will be joules, this is volume, joules per meter cube. So energy density unit will be joules per meter cube. You can see from the graph we can find energy density, from the area, from the gradient we can find Young modulus. Then we will go to elastic hysteresis. You see what is meant by elastic hysteresis, especially for rubber material. We see we will take a rubber band, and when you apply a force to rubber, we know that extension comes delta x. If you draw stress strain, or we can take as force extension graph, we will take it, that is easy. When you apply force with force and extension, if you draw, the shape of the graph will be like this. You can see this shape of the graph for rubber is totally different from other materials. You can see they are not following the same path. So this is we call load-in graph. And the other part we call unload-in graph. So I will denote these points like this way. I will take A, B, C, D, E. So what is this ABCD? What is this area ABCD? Area ABCD. That is the area under the graph while loading. We can say work done when loading. So when you do work, we know energy stored, that is we call as we can say that strain energy stored when loading. Strain energy or elastic strain energy stored when loading. And what is this area? AECD. Area AECD. That is work done when unloading. Work done when unloading. So work done when unloading means we can say strain energy released when unloading. Strain energy released when unloading. You can see that work done when loading is greater than work done when unloading. That means you can say difference between these two areas. I will take A1, A2, this A1 minus A2. What is A1 minus A2? A1 minus A2 gives, we can say A1 minus A2 gives energy, we can say energy, we can say stored. Energy stored when loading and then unloading. So energy stored when loading and unloading. That is we call strain energy. That is we call as stored energy, we call as thermal energy. Thermal energy or heat energy. So, energy stored when loading and unloading gives the so you can see that thermal energy or heat energy. The energy will be stored in the rubber cord as thermal energy or heat energy. So that's why when you do rubber band, many times when you are just stretching and releasing, the rubber band becomes warmer because some amount of energy will be converted to heat energy. Heat energy. Okay. So we have finished the entire topic of solid materials. So we are going to discuss a worksheet of solid material. Thank you very much, students.